ultraviolet minus blue. So integration by parts. Again, depending on how you saw it, the way I do it in my classes is we choose what U is, we choose what dV is. So in this case, U would be T, and dV would be e to the t dt. And then we go down, take the derivative here, du is dt, and v is e to the t. And then we do the formula for integration by parts, which is uv minus integral v du. Does that look familiar? So what would that be? It'd be t e to the t minus a new integral, which would be v du, so e to the t dt. And the antiderivative of e to the t is just itself. So the antiderivative of this should be t e to the t minus e to the t. What are all of those missing, though?
Plus c.
Plus c, right? Don't we always have a constant on all of these? Like each one of those integrations, I should have said plus c, plus c, plus c, plus c. So what I'm going to do instead, if I may erase this, can I erase this yet? Yeah, okay. Is instead of adding constant, I'm just going to do this. It's a constant vector, right? You could imagine that this vector is actually a three-dimensional vector. It's like C1, C2, C3. And so if I took this vector and I added it to this vector, then I would have 1/2 t squared plus C1. So that would be the constant attached to this one. Then this one would have a C2 and this one would have a C3. Got it? Okay. So that's what R of t is, isn't it? R of t equals this. Now I'd like to nail down what these constants are. So to do that, I'm going to use the given information. I know that R of 0 must be 1, 1, 1, the vector 1, 1, 1. So let's plug 0 into this. What is R of 0? Into my vector function, I get what? 0, 1, -1. Plus some constant vector, right? Must equal what? 1, 1, 1. Understand what I did there? Now solve for the constant vector. Don't you just subtract both sides right there of that equation? Just subtract. So the constant vector should be the 1, 1, 1 vector minus the 0, 1, -1 vector. So it's like you're subtracting both sides of this, which is what? 1, 0, 2? Questions? No? You know what? Let me make sure. Did I press record? I did, right? Yeah. I ordered a new microphone. A new, you know how I wear this ridiculous thing? I ordered a new one. I finally invested in a nice one. So I only did it because the damn little battery case I have to take off every time broke, and so I have a rubber band on here now. And so, all right, final answer. R of t is 1/2 t squared, right? Then we had here, I'm going to leave some space, e to the t, and then we had t e to the t minus e to the t, like that, plus our c vector. But our c vector is this. So what I'm going to do is take each of these components and put them in here. So this one will be plus 1, right? This one will be plus 0, and this one will be plus 2. That is the actual position function. We could double check it real quick. If we plug in 0, we better get 1, 1, 1, which I'm sure we will. And if you take the derivative of this, you better get this, which I'm sure you will. Question?
So for every time we don't have definite interval, or like where you go from one point to another, you want us to do that?
Yes, if you're integrating a vector function and you're not given limits on t, then it is an indefinite integral, and you will have like a constant of integration. It'll be a vector of integration, actually. Yeah, a constant vector of integration. All right, we keep going. Applications. So what the heck does it mean, right? Well, if a of t is the acceleration function, right, then the antiderivative is the velocity function. And then, of course, the antiderivative of the velocity would then be the position. So we just did that. There's a way to recover from the acceleration function back to the position. What's the difference between this one and the previous one?
Third component?
Yeah, okay, so that's a different function. But as far as what we have to do, we have to get back all the way to r, but we're starting where? At a, right? I don't think I'm going to work through this one. That's why I'm talking about it. So, but let's talk through it. What we'd first do is integrate this, right? And that would give us v of t. So we would get like integral of r of t dt would give us v of t, and we would be within some constant of integration, right? We would get this constant by using this, what we call initial condition, on v. So then we'd plug in 0 to the v function, then we'd figure out what the c is, just like we just did. Then we have our new v. Then we go back and we integrate that one to get r. Yes?
Should it be R or A?
Where? Yes, thank you. Did I? Yeah, I don't know why I said that. Thank you, Kieran. Kieran's always checking my work. I appreciate that. Integrating the a to get v. And then integrate v to get r. Yes or no? Okay, just, yeah, twice of what we just did. Oh, what would you do, though? What would you do if this right here weren't v? What if they gave you something like r of 1 is the vector 2, 3, 5? Ooh, what would happen then?
We would have C and D.
We would not be able to nail what c is, right, on this first one? So that's okay. We would integrate again. So what would the antiderivative of a constant be? So what's the antiderivative of the C1, C2, C3? What's the antiderivative of it? C1t, C2t, C3t. You see how that would be a little bit different? Okay, so just be careful on that. I'm not asking you that here, but I don't even think that shows up in the homework, but that's the way you would do it. Okay, I don't know if that matches up with what I have on your handout sheet, but we're ready to move on. Okay, arc length and curvature. This is more applications of derivatives and integrals. Lots of notes here. Arc length of a vector function. A few little subtleties I have to make sure you understand before you start using this formula. You've got a vector function, r of t. It has two component functions, f of t and g of t. Let's say that that's a two-dimensional curve, right? If t varies from a to b, so it's like you're starting the clock at time equals a, and then it starts drawing the curve, and you stop it at b. That curve lives in two-dimensional space. Then the arc length of the curve is going to be given by this formula. But it's important that you can only traverse the curve one time. I'll give you an example of a two-dimensional curve. This one right here, r of t is cosine t sine t. We know that draws a circle, right? It'll draw the full circle on the interval 0, 2 pi, won't it? That'll draw me a full circle. But if I go from 0 to 4 pi, it's just going to draw me a circle on top of a circle. That means I've traversed the same path twice. This formula will only work if you're traversing that path once. Got it? So it's not going to account for the fact that you've gone over yourself. It'll mess up. The formula will mess up. So we want to be careful that what we're drawing is never overlapping itself. But if it's not overlapping itself, you're traversing the path just one time, then the length of the arc, that means you take that curve off the page and you stretch it out and you get out your ruler and you measure the length of that curve. It is given by this formula. It is the integral from a to b of the magnitude of the derivative of the vector function. And that is it. And that's awesome. Because that means if you can find the derivative of the vector function, which I think you can, derivatives are pretty clean, and then you can find its magnitude, the magnitude of a vector is the square root of all that junk, right? Then you're in business. And why does this work? Do we care? Do we want to know? I mean, why is it working? I'll try and explain without eating up too much time. Let's say we have this curve that lives in two-dimensional space, all right? And I'm going to make it a true curve that's not necessarily even a function of x, right? That's not a function of x? No? So what we're going to do is we're going to imagine we're trying to find just the length of this portion right here. And let's just say like we've zoomed in like 1,000,000 times. So we're looking at an infinitesimal little portion of the curve. If I can find some way to approximate that length, do you agree that that would be an approximation, a decent approximation of this little arch right here? Yeah? And the further I zoom in, the better my approximation gets? Well, what we do is we can approximate this length with the derivative vector, and its length, the length of that black one. So the derivative of it runs tangent, doesn't it? So essentially this integral is saying we're going to take all the little lengths of all of these little tangents on an infinitesimally small little interval. We're going to take all the little lengths of all these little tangents and we're going to add them up. That's what the integral does. It adds them up, right? And the dt here also comes into play with some triangle stuff that we would have to do to make sure we've got a good approximation. Add them all up and that gives you the length of the curve. Now, like I said, that's just a real quick glimpse into it. How many of you in your Cal 2, you all focused a lot on kind of the geometry of taking something and cutting it up and adding up the pieces? Was that not really made important? Isn't important? Okay. I know in my class that's like the one thing I do is make sure that everyone understands that this integral comes from the idea. Let's see. Should I quiz my Cal 2 students, even though they already passed? This integral gives you the area under the curve, right, everyone? But what's really happening here, let's see, Cal 2 students, this f of x really represents what? The height of some arbitrary rectangle? Yes. And dx represents the width of it. And if you multiply the height times the width, you get the area of that little piece. So this is the area of an infinitesimal rectangle. And then the integral adds them up, infinitely many of them. If you don't have that connection, then this, what I set up here, is going to seem like complete, like, what are you talking about? That's all this is doing. This is adding up arc lengths. It's adding up little derivative tangents the whole way around. Okay. Y'all doing all right? Okay. So let's do an example. Anybody know the answer to this? 12?
What did I just say?
Something, right? Come on, without doing the work, someone tell me the answer to this. 1? Look at what it is. What does it draw? What's the arc length of the unit circle? What's the length of it is the circumference, isn't it? 2 pi? 2 pi r, but r is 1. So the answer should be 2 pi. Let's see if we get 2 pi. So according to what I said, we need to do the integral from where to where? 0 to 2 pi of the magnitude of the derivative, right, of this vector function. Well, let's do that work on the side. What's the derivative? Negative sine t, cosine t, right? What's its magnitude? Square root of, how do you find the magnitude of a vector? Square root of each component squared. Sine squared t plus cosines. Ooh. Ooh, I like that. Because that's 1. Isn't it? Nice. So I'm just integrating 1 dt. What's the antiderivative of 1? T. So this is just t evaluated from 0 to 2 pi, which is 2 pi. Got it? But with this formula, you could actually draw less of it and figure out the arc length, right? So like if I wanted to, let's say I wanted to take, here's my unit circle. What if I only wanted to know like this piece right here? Let's just call this, I don't know, let's call that S. And let's call this in here, this is, let's call that T, kind of like for theta. Then how would this integral change? Okay, the bounds would go from 0 to where?
0 to
Well, I don't know what that angle is, right? But what am I calling it? T. Do y'all understand? Let's call it theta, so maybe it'll make a little more sense. Theta, okay? Because that way you don't mix it up with the variable in there. And then this would change, right, to just be theta. And this would change to be theta. And this answer would change to be theta t, right? In other words, you would have this. S would be equal to theta t, wouldn't it? Y'all follow that? Hold on. No. Sorry. What did I mess up there? Theta goes in for t. So it's just theta. So S would be theta. You might be asking me why I did that. I want to change the problem. That's why I want you to see something. Did you all kind of follow that a little? Okay. What if I have not a unit circle, but a circle with radius r instead? How does my vector function change? R cosine. So we would have r cosine t, r sine t. I should put the r in there. Right? If I wanted to find the length, that length right there, I would still go integral. I'd still go 0 to theta, right? And I'd need to find the magnitude of the derivative of that. So let's do a quick derivative on that one. What's the derivative? Negative arc sine t, right? And then r cosine t. What's the magnitude of that? Square root of r squared sine squared t plus r squared cosine squared t. What can you factor out of both of these? R squared, and then you get the 1 to come out. Square root of r squared? R. You would just get r, wouldn't you? dt. What's the antiderivative of r? With respect to t. Yeah, right. RT. Plugging in 0 and theta. I know I'm working through this fast. R goes in for t, r theta. And you plug in 0, you get nothing. So that would mean that S is what? R theta. Does anyone remember that formula from pre-cal?